Hello, everyone, and welcome back. So, we are starting a new module which is called Stochastics. Today's lecture is about stochastic processes. And as you may know, stochastic process is the fundamental building block of quant finance. All right. Just a quick audio check. You guys can hear me properly? Okay. All right. Maybe there is some issue on your side. So yeah, we are starting this new module called stochastics. It's the fundamental building block, and the ultimate target for us is to be able to model financial variables, right? Stock price, interest rate, FX rate, commodity prices. Everything will eventually be modeled as a stochastic process, right? So you model the underlier, which is the stock price, commodity price, FX price, as a stochastic process, and then you can derive prices of derivatives. Okay, but for us to be able to do that, you need to understand stochastic processes in and out. Okay, so we will be spending a lot of time understanding the theory, and there will be lots and lots of practice problems. You have to practice uh, various calculations in stochastic process so that you have a very good handle on the this particular topic. That is absolutely crucial. Without that, you will not be able to understand the formulas. You'll have to memorize them. Nobody wants that, right? So pay attention. This is an exciting topic, extremely important topic. Without this, you cannot even hope to proceed to understand derivative valuation. All the future modules are based on this. Okay, so that's one. Right, so we'll be solving a lot of practice problems, and yeah, keep the momentum, and let's get going. I have personally tried my best to add lots of exciting examples along with animation. Animation is important because if you see the textbooks, you'll only see text after text after text with a lot of notations, right? But I feel all of these have a very good, you need to have a very good visual understanding. The moment you see a stochastic process, there should be an image popping up in your head. At least that's what happens to me, right? And it is important to have that image in your head. It will help you understand the maths a lot better. So every class I will show you animation for you to understand these topics better. So I am doing the hard work. I expect you to also do the hard work. Okay, do not take this one lightly. All right, so let's start with this topic, stochastic processes. Okay, so we what is a stochastic process? The definition of stochastic process is it is a set of ordered random variables. Set of ordered random variables indexed by time. Okay, so I mean, from a layman perspective, we all understand random variables, right? Capital X is a random variable. We understand that. It can be discrete, it can be continuous. We know so many different types of distributions that we can use to model a particular random variable. Stochastic process is nothing but it's a list of random variables or a set of random variables. Okay, it's a collection of random variables, but they are ordered. Okay, there is a specific order. You cannot just swap the orders. So it's just a collection of random variables. Each of those random variables is indexed by time. Okay, so that's what a stochastic process is. So let's say xt is a random variable which models the value of the stochastic process at time t. So when I write xt or xt, these are two different ways you can write it. Same thing. It means the value of the stochastic process at time t. That's all. Okay. So collection of random variables indexed by time. That's what you need to remember. All right. Now, what is xt? Xt is the stochastic process that we are using to model something. For example, xt may be stock price. Stock price at time t. Okay. Now, if you look at this picture, this is the typical scenario that you will always have. Okay, so there is a time point which is right now. So you are standing here right now and you are monitoring or observing a particular process at certain time intervals. Okay, so starting with this x0, x1, x2, x3, all of these are actually random variables, right? Remember, stochastic process is a collection of random variables indexed by time, xt, that's what it is, indexed by time. Now if you're standing right here, then the x0, x1, x2, x3, x4 are not really random because they would have already been realized. Stock price, till this point you have the observations, right? It's not random anymore. So that's why for x0, x0 has taken a value small x0, x1 has taken a value x1. Remember, we write capital X for random variable, we write small x for values, the values it can take, right? So if you're standing here, x0, x1, x2, x3, x4, all of these random variables have been realized, and these are the realized values x0, x1, x2, x3, x4. Okay, this is in the past. You have the data points, there is no randomness in it, it is known, everything is fully known until this particular point. Okay, so this is the past. Now what happens in future at different these time points, t equal to 5, t equal to 6, t equal to 7, etc., etc., x5, which is the next value of the stock price. So the grid depends on how you want to discretize the time. We'll talk more about it. It could be daily, weekly, monthly, right? Or even more frequent. Irrespective, right? Whatever discretization you want to do with respect to time, that is a modeling choice. But x5, x6, all of these guys are random variables. All right, x5, x6, x7, these things are not known, so these are random variables. Right, so please understand this particular picture. Some of the realizations have already happened and some are still random, so this is all in future. Okay, now from a modeling perspective, what we tend to do is we have all the past data points. Okay, using that, we will fit a model to describe this stochastic process, and that model will have some parameters. Okay, so we're looking at the past, we estimate the model parameters, and then our model is ready to predict the future evolution. Okay, that is the crux of modeling. All right, I'll pause here. Any questions on this? Stochastic process, past, present, future, what's known, what's random, all of these must be clear to you. All good? Any questions on this, or can I move on? Clear? Okay. All right, let's move on. Now let's talk about time domain and state space. All right. So we described a stochastic process. Stochastic process is a collection of random variables. Now we can write it like this. This is a collection of random variables where the time t belongs to a set j. Okay. J is called as the time domain. You look at this as from a function perspective. For every function, we have a domain and a range, right? Domain is where the function is defined, and for every point in the domain, which is the input, you have an output, and all the outputs are collectively called as range. Correct. Similarly, here also, the input would be a time is called as the time domain, because for every t we have a corresponding xt. So this collection of t's or the domain of t is called the time domain, and the values it can take is called as the state space S. Okay. All right. So we definitely, so whenever you define a stochastic process, you have to define what is the time domain, what is the state space. Now, the set of random variables that we saw here, right? Here, these are still random, guys. Okay, from here to here, all of these are random variables. Now, these random variables may be dependent on each other. They may be independent also. Okay, depending on the type of stochastic process. So, in order to fully specify the stochastic process, you have to specify the joint distribution of these random variables. Joint distribution. It's simple. See, how do you define a random variable? Through a PDF, correct? A normal random is fully defined when you specify the probability density function. This is the mu, this is the sigma. Everybody knows what the PDF formula is. Once you define PDF, you define everything. You can find out expectation, you can find out variance, all other things, right? So if we want to specify the stochastic process, you have to specify the joint distribution of the random variables, because it's not just one random variable, it's a collection of many random variables, right? So for example, x7, x8 together, I need to be able to tell you what is the joint distribution of x7, x8. It will be a bivariate distribution, some distribution, right? So when we are trying to model, you should be able to tell me what is the joint distribution of the random variables. Okay, so if you are able to do that, then you have specified the process, right? So that is what I've written. For example, find the distribution of x9, x10 together, right? Doesn't have to be two variables. It's actually, all variables put together, how they jointly behave. Once you specify that, you are done. Everything else can be calculated. Okay. All right. Now the random variables in the set may be identically distributed as well, right? Or they may not be distributed identically. They could be coming from different distributions. So x9 has its own distribution, x10 has its own distribution, right? They may be different or they may be identical. If they are identical and independent, we refer to them as IID. So this is probably known to you. We use it all the time, and IID is a very important assumption. It makes life simpler. That's all. Okay. So if the random variables are coming from identical distribution and they are independent, it is called as IID. Okay. So yeah, let's do one. So here's one question. Let's say we model S&P 500 daily closing price each day by the process XT. So we are monitoring S&P 500 daily closing price. Okay, that's my XT. So X1, X2, X3, X4. Question is, are the state space and time domain discrete or continuous? Okay, there is a question from Arka about stationarity. We are not there yet. Just hold on a little bit. Let me introduce stationarity, then I'll get to your question. So let's do this one. If you're modeling S&P 500 daily closing price, pay attention. By the stochastic process XT, what is the state space and time domain? Is it discrete or continuous? So we have price is continuous, but time is discrete. Okay, interesting. Price is continuous. That means state space you're saying is continuous, and time domain you are saying discrete, correct? Anybody else want to comment on that? Anybody wants to differ? Okay, Amit says both are discrete. Interesting. Any other? Okay, let me explain. Actually, both of you are right. It's tricky, right? So when you say daily closing price, that means your recording frequency is daily. Okay, day one, day 2, day 3. Every day at the end of the day, you're looking at the closing price. So definitely time domain is discrete, right? It's not continuous because you are observing day by day. At the end of the day, what is the price? Now looking at the state space, which is the what all values the random variable can take. Okay, S&P 500 closing price. Now, is that discrete or continuous? So here's the thing: if you are looking at reality, I mean actual quoted price on the market, it is discrete, right? Because the stock prices move in ticks. So, right, 102.50. You will never see a price which is 100.222336655. That does not happen, right? So, in reality, prices move in ticks. So, if you're, being like really literal, then it is discrete, right? But if you model stock price as a discrete variable, it'll be a nightmare. How many levels are there? Tell me. If you model stock price as a discrete random variable, how many levels you will end up modeling? So in discrete random variable, what we do, we have possible values and their corresponding probabilities. That is how we define a discrete random variable. In case of stock price, how many discrete levels would be there, right? There are tons of different ticks. It is not practical. It is not practical to model stock price as a discrete random variable. We would rather approximate it as continuous random variable. Stock price should take any possible value. And then maybe round it to some nearest tick. That is the proper modeling approach. So practically, if I want to answer this question, it would be discrete time, continuous space. But if you're being too literal, like exact behavior that we see in the market, then both will be discrete. Discrete time, discrete space. But this is not a preferred modeling approach. Okay, when there are so many discrete levels that you have to manage, better model them as continuous and then approximate. That's the go-to approach. Okay. All right, awesome. Let's move on. The same topic, right? Choice of discrete versus continuous. How do we choose? The exact theme that we just discussed. So stock prices change frequently, but by minimum tick size. Correct. So as per reality, the state space should be discrete. However, managing so many discrete levels or discrete states and their associated probabilities might be difficult to model. Okay. So it's a modeling preference. We would rather model stock price as a continuous random variable. And the second aspect is about the time domain. So we said daily closing price. We are monitoring only daily closing price. That way it becomes discrete. But daily is not the only choice, right? So for example, if you're doing, let's say, high frequency trading, then you need minute by minute price, correct? So your time domain becomes again 0, 1, 2, 3, 4 discrete, but at a very frequent interval, right? So the how you want to discretize the time domain depends on multiple things. It depends on the limitation of your device or measuring apparatus, let's say. That is one. Other constraints or even your use case. What are you trying to model? What's your requirement? Based on that, you choose a suitable scheme to discretize the time domain. Okay. So for example, if you're calculating 1 day value at risk, I know we have not talked about value at risk yet. It's just a risk measure that you calculate. In 1 day, how much can you lose? That's the high level definition of value at risk at some confidence interval. If you want to measure 1 day value at risk, do you need minute by minute stock price detail? It's an overkill, right? You don't need high frequency data. You just need daily closing price. That is sufficient for you to model how much you can lose in 1 day. So the frequency matches with the use case, correct? So that is one. If you are doing monthly evaluation of something, then you need a monthly frequency data point. You don't need daily, right? And the second thing is, yeah, device. So let's say you are trying to measure the temperature. If you're trying to measure the temperature, it is limited. See, temperature in reality is a continuous thing, but when you are measuring, you are using some kind of digital gadget or something, right? And it only gives you a specific data point, so 32.18 degrees Celsius. You never get a point which is 32.11113360. That's not practical, right? So it might be limited based on the device that you're using. Okay, so all these are different considerations. What modeling choice is appropriate, okay, given a particular use case, right? So that's how you decide whether you want to do it in a discrete way or continuous way, both time as well as state space. We'll talk more about this. Okay, and yeah, so here's the final note. In stochastic modeling of financial variables, right, interest rates, stock prices, FX rates, it is common to use continuous model. Why we prefer continuous model? You can do discrete also. In fact, we'll study a method called as binomial tree method, which is a discrete model of stock price. But we prefer continuous. Why? Because if you use everything as continuous, then you can use calculus. Calculus is a study of continuous variables. You have to have, because we are talking about infinitesimal change, right? So everything should be continuous. Time should be continuous, state should be continuous. Then you can use calculus as is, right? And calculus is so beautiful. So we want to use calculus. That is what stochastic calculus is all about. So it is the study of stochastic variables or stochastic processes using calculus to um, treat the stochastic process. That is stochastic calculus, which we'll be discussing next class. Right. So preferred approach is continuous because we can use, then you can use calculus. Right. Okay. So yep, choice of discrete and continuous. Now here are some examples. Now we're talking about two things here, right? Time domain and state space. Time domain and state space. For both we have the choice of discrete or continuous. So how many combinations you have? There is time domain, there is state space. Both of them can be discrete or continuous. Total number of combinations is 4, exactly, right? So we have 4 variants. It's so nice. Discrete time, discrete space, discrete time, continuous time, discrete space, continuous time, continuous space. So let's look at some of the examples in real life which are amenable, or they fit into a particular modeling choice. The first one is discrete time, discrete space. One probably very familiar example, which is modeled under this assumption, is the rating migration, credit rating migration, right? So we know there are rating agencies, right? There is S&P Global, there is Moody's, there is Fitch. All of them rate listed companies in a scale of discrete set of ratings, right? So if you look at S&P Global, there is AAA, AA, A, triple B, blah 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 blah. This is the default category. So eventually, all companies need to be rated with one of these categories, correct? Right. So the variable that we are modeling is credit rating. That's the stochastic process, credit rating. This is my XT stochastic process. Now, at different time for a given company, let's say IBM, at different time, IBM would have different ratings, correct? So that's the stochastic process. Now, the time domain is discrete. Why? Because the ratings do not change continuously. There is a quarterly evaluation. You can do quarterly or yearly, it doesn't matter. But every quarter, S&P will review the entire, balance sheet, growth prospects, business, everything, and then come up with a rating. So every quarter, you will see the rating update. Rating will only get updated or change every quarter, not in between. It's not a continuous thing, right? So that way, time domain is discrete because it has a quarterly frequency. And what all values the credit rating can take? Only these values, discrete set of values. There's nothing outside of this. So the space is also discrete. Discrete time, discrete space. Okay. When you are dealing with discrete time, discrete space, typically we use um, something called as Markov chain to model it. All of actuaries are based on this idea. Okay, Markov chain is the bread and butter of for actuaries. I use another term, Markov here. We'll talk more about it. It has to follow Markov process and it has to be discrete time, discrete space. Then we can use Markov chains. Okay, so we basically we use transition probabilities from one state to another, and that's Markov chain. So discrete time, discrete space, and example. Is it clear? The better you understand these fundamentals, right, it will be a cakewalk going forward. It's not difficult. Is this example clear, guys? Discrete space, discrete time. Okay, let's move on. Next one, continuous time, discrete space. Continuous time, discrete space. That means there is something that you are measuring which can only take discrete set of values because it is discrete space. But the change in that value can happen anytime. There is no fixed like frequency. It's a continuous time domain. So the update or the change in the stochastic process can happen anytime. So example, the easiest example I can give is customer default use case. Customer has taken a loan. The state of the customer is either good or bad, default or no default, correct? So the state space is discrete, only two values, default or no default. But the status can change at any point in time. Customer can default at any point in time. Correct? So this is discrete space but continuous time. Another example would be for insurance companies, right? When they sell a policy and you pay the premium, you are the policy holder. Insurance companies will see you or the policy holder as somebody who has these three states: healthy, sick, dead. Three different states. Right? If it's healthy, then you are just earning premium. There is no outflow. You're happy. You're happiest when the person is healthy. He's just paying premium. When you become sick, then there will be medical bills and all the stuff, right? Which you have to compensate depending on the insurance policy that you have sold. And this is the biggest outflow, life insurance, right? So this particular choice of states is important for insurance. But now the state space obviously discrete. There are three possible states: healthy, sick, or dead. But looking at the time domain, that is continuous. It's not like you fall sick only at the end of every quarter or something, right? You can migrate between healthy to sick to dead at any point in time. Continuous time. Continuous time, discrete space. Okay. Continuous time, discrete space. This one is called, if the process is Markov, which is something we will learn a little later today, then this is called as Markov jump process. That was Markov chain, discrete, discrete. This one is Markov jump because suddenly from healthy you will jump to sick state. So that's Markov jump. You need a continuous time but discrete state to have a jump, right, from one state to another. So this is continuous time, discrete space, guys. Okay. The next one, discrete time, continuous space. Discrete time, that means something that is happening at a regular interval. It is not continuous. Discrete time. But space is continuous. That means the values that the stochastic process can take is anything possible. Any value is possible. Any value is possible. Continuous space. Okay. The entire time series literature is actually based on this construct: discrete time, continuous space. All the time series that we deal with, right? So, obvious examples is GDP, unemployment rate, um, even so anything you want to model using time series infrastructure like auto regressive process or moving average process, ARIMA, SARIMA, SARIMAX, right? I uploaded a time series video lecture also in Python, so take a look at that. All time series processes follow this discrete time continuous space because the value that y can take is any possible value, but you are always modeling them on a daily basis or monthly basis, so that's why it is discrete time. For example, gdp growth rate is published every quarter. Unemployment rate, I took this from Fred St. Louis. It's a very good website that gives you authentic data points for all macroeconomic variables. Okay, anytime you want to do a project, go to Fred St. Louis. You'll find everything. It's authentic. It's accurate. Right? It's free. So this is the unemployment rate for the last I don't know, from 1948 to 2025 at a monthly frequency. So that's why this is discrete time. But the value of the unemployment rate can be anything, right? It's not discrete, that is continuous. So discrete time, continuous space. All of time series follow this, okay? Time series modeling follow this, discrete time, continuous space. And then finally, continuous time, continuous space. So something that can change at any point in time. And the values it can take is also anything. Continuous space, continuous time. The best example of this is Brownian motion or Wiener process. Brownian motion or Wiener process. This particular entity is continuous time, continuous space. And this is the star of the show of stochastic calculus. Stochastic calculus is something which is the natural extension of this particular topic, right? That is what we will be doing lots and lots of practice. But the key variable that you are modeling as part of stochastic calculus is this guy, Brownian motion or Wiener process. Okay. So this one is continuous, in continuous time, in continuous space. Yeah, we'll learn all about this. Actually, next class would be tomorrow, would be on Brownian motion. Okay, so more to come on this. Yeah, any questions so far, guys? All good? Okay, perfect. Now let's move on. Question. So you are thinking of moving to live in Edinburgh. As part of your research into what it is like to live there, you're doing some research before you move to a new city. Obviously, you want to look at the weather, the cost of living, the crime rate, blah, 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 right? So these are the data points that you have collected. The maximum daily temperature every day since some January 1st, 2006. Whether or not it has rained each day, right, from this particular date. The number of random data points, right? The number of cyclists that got injured in road accidents since this point. So we want to identify the time domain, the state space, comment if it's discrete or continuous, and then sketch the plot. Okay, that's the exercise. So let's do the first one. Maximum daily temperature each day. Let me go here. Max daily temperature each day. Can you tell me the time domain? Participate fast. So, DTDS. Okay, great. Time domain is discrete because it is every day. And since it is temperature, I mean, yeah, it's continuous space. Right. How do we plot this? So at discrete time points every day, you will have some value, max daily temperature. This is the plot. It's a scatter plot. On the y axis, the space, it is a continuous value. This is temperature, right? Temperature, this is, you can write day, every day, day or date or whatever. Now, here is the small things, okay? Small things, but important things. Can I do this? Is this correct? This is not correct because then you are saying there are values in between the dates. That is not possible because you are only measuring at discrete time. The value is available only at discrete times, not in between those. However, you can still do this to realize the shape of the curve. This is just to understand the shape. What is the shape? Is it linear, quadratic, exponentially increasing, decreasing, all those things? Once you've, right, you have to interpolate to understand the shape. But I mean, uh, truly speaking, there is you should not be doing this. There is no data, please remember. But you are doing it for a visual understanding of how the shape looks like. Okay, that is allowed, but there is no data point. Okay, please remember, it's very important. Second, did it rain rain or not? Um, Rain or not every day? Please tell me. Time, space, discrete time, discrete time, discrete space. Okay, what is the space actually? What is the state space here? State spaces is a set of two possible values, 0 or 1. Rain or not. Bernoulli, right? Two values, rain or not. And J is your time domain, which is 0, 1, 2, blah, 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 blah. Every day you are measuring the state. How do we plot this? Same thing as above, no difference. So you have time here every day, and this. So let me shift the y-axis so that you can. So let's say this y coordinate is -1 here, and this is 0, and this is 1. So every day either you are here or here. Two possible values. Okay. There's nothing in between. So discrete time, discrete space. All right. Number 3, number of cyclist injuries from road accidents. You're counting number of accidents, let's say. Number of accidents. This is tricky, guys. So think a little bit and tell me what is the time domain and state space. Number of accidents, number of road accidents. Okay. Arca says continuous time, discrete space. Discrete space, continuous time. Okay. Any other answer? Continuous time, discrete space. Yes, that is correct. Continuous time, discrete space. Why it is continuous time? Well, there is no fixed time for accident, right? It can happen anytime. You can have 10 different accidents on the same day. It can happen any second, any minute, right? Continuous time. Accidents can happen at any time. Same as default, customer default, remember? Or healthy, sick, dead model. That's also um, continuous time because it can happen at any time. Discrete state. Why did we say discrete state? You're counting number of accidents. It cannot take a value 2.5. It cannot take a value 3.1. It can only take values. So let me write it. State space is discrete. The values it can take is 0, 1, 2. You're counting number of accidents, right? It start with 0, no accidents, and then keep counting 1, 2, 3, 4, how many accidents. They're still discrete. Although it's an infinite set, but it is discrete. And the time domain is continuous. Time domain is continuous. You can write it as, let's say, R. Okay. So, good. So, you understood this. How do we plot this? This is important. How do we plot this? So, time is continuous, guys. Okay. I will not do this stuff. This is not correct. And state is discrete. So, you start from 0 and then you're keeping a track of the count, right? So, it will go like this 0. Then suddenly there is an accident. So, your count goes up. So, this is 1, 2, 3. This is 0. Jumps. No accident, no accident. Another accident. Another immediate accident. Step function. Question from Rishabh. Continuous time. Could you reply in the group so that everybody can look at your question? Continuous time is not clear. It's very simple, guys. See, think very, very, this is common sense. When can accident happen? Tell me. When can an accident happen? Is it any time or only after, let's say, weekend? Every week you can have an accident. Any time, right? So if any time something can get updated, which is the count of accident, that can get updated anytime. That's why it is continuous time. If accident only happen on Sundays, then it would be discrete time. Okay. Right. So yeah. So I hope this is clear. Yeah. Awesome. Now let's move on. So good with this question. Okay. Now this is interesting. Sometimes we have a mixed type. Mixed type basically means that you are combining two different types of stochastic processes together. Okay, to accurately model something. Okay. So for examples, let's consider this. Suppose you are running a car business and your source of revenue is from two different sources. Okay. One is direct sell. When you're selling a car, expensive luxury car, okay, you're getting 40,000 or 50,000 euros per sale of the car. So each car sells between these two values. Between 40,000 to 50,000. That's the price, because there'll be negotiation and stuff, right? You cannot pinpoint that these are the prices. So what I'm hinting is it's a continuous space. Car sales price is a continuous space. There'll be tax and all these things, and eventually you'll end up with a number which is like 42,560.28 or something, and then you ignore the pennies, whatever. So it is a continuous space, a big price, low volume. Car sales is not very a frequent thing, right? It will happen maybe 2 a day or 1 in 3 days or something, right? So high price, low frequency, which is a source of revenue, right? Sale, revenue from sale of the car. But then parallelly also, and you sell, let's say about 10 to 20 each year, because you are a luxury brand. But on the other hand, the lifeblood of the business is the regular servicing and maintenance of the cars that you already sold. The cars that you have sold so far, they are coming to you for maintenance. Change the engine oil. There is, top up the the washing fluid and blah 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 and maintenance, right? So that is a more frequent small price transaction. Lot of transactions every day. Maintenance service would be like all the time, right? Every day you might get small maintenance service requests. So that is kind of a continuous stream of cash flows. Okay. So your overall revenue is a mixture of these two sources. Correct. So revenue balance is a mixture of two stochastic processes. A lot of regular small transactions coming from maintenance and service. Okay. So this one would be continuous state because the value of the transactions could range from $10 to, let's say, $1,000 depending on what kind of servicing you are doing, right? Small values. So better to model them as continuous. And um, and it's continuous time as well, because maintenance and transactions can happen anytime. So it's a continuous time, continuous state kind of. So you have to model the maintenance part of it using a continuous time, continuous state stochastic process. And the second one is okay, so here I have each car sells for, you know what, there is a little, let me cross this one out. So each car sells for, let's say, either 40,000 or 50,000, right? Then you have a high value discrete sale revenues. So that is discrete state, because either it can be 40,000 or 50,000. Let's say there are two types of brand, the BMW and some particular model, and then Mercedes, and there are fixed MSRPs. Let's go by that, okay? So discrete state, but continuous time. High value revenue items, which are discrete, but it is also continuous because sale can happen at any time. Sale can happen at any time. Both are continuous domain, okay? So your overall revenue balance is a sum of these two processes. So you need to combine two different stochastic processes to model your variable of interest. Okay, it's a simple example. A more practical example is this one, which we will get to a little bit later. So sometimes when you model, say, stock price, okay, typically we use diffusion process. Now it will not make sense to you, but maybe after a few lectures this will make sense to you. Diffusion is through Brownian motion, which is like a continuous evolution of the stock price. Okay, remember, Brownian motion is a continuous state, continuous time process, right? So whenever you are using Brownian motion to model something, you are enforcing that stochastic process behaves continuously and takes continuous values. That is called diffusion. Okay, but at the same time, we started with diffusion. In fact, Black-Scholes model is using geometric Brownian motion to model stock price. That is the starting point. But then people realize, practically speaking, stock prices also suffer from jumps, in the sense that the price is 120, suddenly there is a market crash and it plummets to 30. There is a 50% jump or something more than that. It's possible. Brownian motion is not able to predict those kind of movements. So what we do is we also add jumps to the stock price model. So it is both diffusion and jumps put together. We are more accurately able to predict or model the stock price behavior. Okay, so that's a mixture of two different stochastic processes. We'll learn more about this and how to price options under jumps also. That is all of those we'll talk about in the upcoming classes. Okay, so now after this class, I want you to go back and start looking at different random processes in real life and think what kind of model you should use. Is it going to be one of those four categories, or it should be a mixture of two different things? Because there are separate stochastic processes that are contributing to that particular variable. So you have to think like that. This is a pure, modeling thought process. Okay, so mixed type. All right. So now, now that we have a handle on continuous versus discrete when it comes to time domain and the state space, that you have to define first. Okay. Once that is defined, the next step we need to perform is actually define the distribution. In order to define the stochastic process, remember our end goal or the target is, let me go back. Yes. So you are here, you are looking at the future random variables, which are unknown. What is the distribution? This is my target. So you have to specify the stochastic process such that I can come up with the distribution of these random variables. That is the goal. Okay. Now, here is the thing. How do we define joint distribution? Through some function formula or something, right? Now, in order to define joint distribution, do you think it is practically feasible to define joint distribution of all of these random variables together? It is not practically feasible. How many random variables will use to, define the distribution? It is practically not feasible. It's a formidable task. So what we do in practice is we define a separate process, an auxiliary process or an intermediate process, which indirectly specifies the stochastic process. Okay. So we define another helping process, helper stochastic process, which indirectly will completely specify the original stochastic process. So let's see how we do that. Okay. Arka has a question. Does it mean a previous stock price distribution shall be similar to predicted stock price distribution? Why we are using joint distribution? I think let's go through this. The things will start to fall in place. You should answer your question. Okay. All right. So let's consider a model where the stock price is a very, very simple model. In fact, we will use this going forward for pricing purpose to start with, right? Simple model where the stock price either increases or decreases by $1 every day. That's the process. See, my original process is stock price, stochastic process. How does the stock price evolve? Okay. And how do I specify the distribution of the stock price? All right. This is an indirect way. I'm saying, forget about the stock price. Think of change in stock price. Change in stock price day by day. Okay. So change in stock price, I'm saying, is very simple model, is either plus $1 or minus $1 every day. That is my model. Okay. And the up move and the down move have these probabilities. The up move has a probability of P. The down move has a probability of 1 minus P. Simple model for stock price. Okay. And we will also impose that the changes are independent. Extremely simplifying assumption. That what this basically means is if the stock price went up by $1 yesterday, that has nothing to do with what will happen tomorrow. Tomorrow I am also, having the exact same probabilities. Probability of up move is always P and down move is always 1 minus P. You can fix P as, let's say, 0.5 or 0.6, doesn't matter. But it is the same every single time. And they are independent. Changes are independent. Okay. Yesterday's change does not affect tomorrow's change. So let the price of the stock price be ST. That's the stochastic process, my target stochastic process, which I want to model. Initial value of the stock price is $100. If you define a process for the change in stock price, which is what we have done right now, we have specified the values. The values are plus 1 or minus 1 with probability P, probability 1 minus P, right? This one is a model for the change in stock price. that indirectly specifies the entire distribution of the stock price process. Make sense? Okay. So that's the idea. All right. Now, this particular model is called as simple random walk process. Simple random walk process, because it is the as simple as it gets, right? How do you what is the minimum in what is the minimum way in which you can model a random variable? Only two states. If you want something as random, right, then you can have, if you have only two states, it becomes random. And the associated probabilities, state 1, state 2, plus 1 probability p, minus 1 probability 1 minus p. It's a random variable, correct? That's why it is simple. Simple random walk. And this walk idea, we will discuss next. What is this walk actually? And I have created everything, the animation in Excel. So I'll walk you through that. The whole thing will be very clear to you. This model is called a simple random walk process. And to make things interesting, there is a barrier at zero. Stock price follows simple random walk process, but there is a barrier at zero because stock price cannot become negative. So it is an absorbing barrier. When we discuss about barrier options, there we'll talk about barriers, but we have a natural barrier here for stock price, right? Stock price can go up, go down, but there is a barrier here at zero. Okay, if it hits this point, basically company is bankrupt and somebody has to bail, then it will go up, but it can never be negative. Stock price can never be negative, so there is a barrier. Okay, what is the time domain? Time domain is measured in days. We are discretely modeling because daily stock price, right? Every day stock price can go up by $1 or down by $1. So it's a daily modeling. So time domain is measured in days: day 0, day 1, day 2, day 3, day 4. State space is also in this case discrete because the stock price is moving up or moving down by $1. You cannot have a value of 100.56. As per this model specifies the stock price as a discrete state space. Correct? The values would be all non-negative integers. From 0, 1, 2, 3, 4. Stock price can take any value, non-negative integers. As per this model, please remember, in reality, maybe a continuous model is preferred because you can use calculus. Here you cannot use calculus because it is all discrete. But as per this model, both of the time domain and the state space are discrete. Okay. But our model is not directly on the stock price. We are modeling the change in stock price through this distribution. You specify the distribution for the change. Remember what I said, auxiliary process. Here the auxiliary or the helper process is the change or the increment. Increment is the textbook word that you need to use. Okay, we have defined the process for the increments. Increments is a change in stock price. Okay, so that is what our model is. And indirectly, we would know everything about the stock price. Okay, so let me formally introduce the simple random walk process. A simple random walk process, YT, in our case it was stock price, but I'm just saying in general it can be any Y. Simple random walk process YT is the previous value of Y plus something. So this is an add-on, right? Whatever was the previous value of Y, you add something onto that. So that is how it moves, evolves. Okay. This XT is the change. Or you can say step. One step. Either plus 1 or minus 1. Or you can say increment. Okay. And that keeps moving the Y. So new Y is old Y plus the step. Now Y is the walk. because you are walking, right? So you are at, that means y actually gives the location or the position of you of the particular variable. And after every day you are somewhere new, right? Either you're up by one or down by one. That depends on what this random variable, what the realization of this random variable. Okay, and the model that we specify is for x, not for y. Y is complicated. The walk itself is complicated, but the change or the increment is very easy to imagine and model, and that is just this: plus 1 probability p minus 1 probability 1 minus p. Are you with me so far? Any questions? Simple random walk process. So far, so good? Okay. Now, the simple random walk becomes a simple symmetric random walk if the probability of up move and down move are equally likely. Okay. In general, it is p1 minus p, but if you say p equal to 0.5, then it becomes symmetric. Simple symmetric random walk. Okay. All right. Now we are getting into, so we'll do a lot of questions, and just I have to, I cannot stress this enough. This simple fundamental random process is the building block. Okay. Once you conquer this, then we can go to some general random processes. Approach is similar, but we should be able to calculate everything under this setup. You should be able to calculate joint distributions, covariance, expectation, variance, anything I give you should be able to calculate. See, what I'm trying to do here is take this topic uh, slowly and do a lot of questions. The better you understand this foundational model, all of the other things are similar. It's just that the manipulation is different, but the idea is same, and you should be able to crack any interview on stochastic process, stochastic calculus going forward. Okay, so try to understand this as detailed as possible. Okay, no random stochastic process is simpler than this. Can you think of a simpler random stochastic process? This is the simplest. So let's understand this in and out. Okay. All right. So we have assumed that the increments here are IID. The XT here is in. Can you tell me why this is IID? I'm saying XT is IID. XT is the increment or the change, right? That's independent and identical. First of all, let's understand why this is identical. So any time, right, at any point in time, suppose this is t, the or maybe this is t minus 1, whatever value xt takes here is either plus 1 or minus 1 with these probabilities. This change and this change, so let's say this is s minus 1 to s, okay, another 2 time points. This change xs and xt are completely independent of each other. Because look at this distribution. This does not depend on the state. It is always plus 1 with probability p, minus 1 with probability 1 minus p. This distribution, this discrete distribution for xt is constant throughout. Okay, and so that's why the changes are independent, completely independent. So what I'm trying to say is, let's say yesterday the move was plus 1. That has nothing to do with what will be the move next day. Okay, still the same distribution applies throughout. That's why it is independent. That's why it is identical. It's also independent because it does not depend on any state. Identical means the same distribution carries everywhere. Values, probabilities, that's the distribution. The same distribution remains constant throughout. That is why it is identically distributed. All the changes come from the same distribution, this distribution. Identical. It's independent because increment at one particular point does not affect increments at other different time instances. They're completely independent of each other. Okay, so this is IID. IID simplifies our life. Okay, so yeah, each increment serves as independent step The series of steps constitute the walk. So we'll see the animation for this and understand everything. And yeah, increments have nicer properties than the process itself. So if you look at the random walk process itself, which is y, that is complicated. But if you look at x, which is the change, daily change, has very nice properties. It is IID, and everything is tractable. This looks like a Bernoulli random variable. Only difference is that in case of Bernoulli, you have 1 and 0. Here we have 1 and -1. That's the only difference. But pretty much you can calculate everything analytically, right? It's very simple. Okay, one question, and then probably let's see, we'll take a break after some time. Is the original stochastic process YT IID? We know X is IID. Is Y IID? That's the question. What is your gut feeling? You understand what is this? The Y, that means the value of the stock price. Stock price is Y, okay? The actual value of the stock price. We are saying changes or increments are independent identical, but is the stock price, all the stock price values at all future points, are they independent and identical? Independent and identically distributed. Are they coming from the same distribution at every? So this is my stock price starting with 100, correct? What happens in future at this point? So let's say after 1 day, after 2 days, right? I'll have some random stock price here. The distribution of stock price here and here, are those identical and independent? Not IID. Short answer is not IID, right? To prove that it is not IID, it's actually very simple. Let me show you. To show that it is not IID, basically, if you can showcase just an example, that is also fine, that it fails the IID condition. Okay. What is, so, my initial stock price Y0 is $100, correct? At time t equal to 0, stock price is $100. What is the probability that after 10 days, my stock price would be $110? Just don't calculate the probability. Just tell me that is this even possible or not? After 10 days, can the stock price be $110? Under which case it will be? If every day it goes up, only that is the condition, right? If every day it goes up, then your stock price would be $110 after 10 days. Probability is very easy to calculate actually. This is the probability, correct? Every P times P times P times P, every day it has to be, going up. Only then I can reach 110. And this is greater than 0. Whatever P is, there is some positive probability, correct? What is the probability of Y10 equal to, again, same, $110? Given that Y1 is, say, 99. Y1 is 99 means after 1 day, the stock price actually went down. From 100, it became 99. From there, what is the probability that I'll get Y10 equal to 110? Impossible, correct? 0. Correct? So that means the unconditional probability of the same thing, Y10. This is the conditional probability, given that I have some more information. If the unconditional probability is not same as conditional probability, then they are dependent. Y10 very much depends on, you can say Y10 depends on, or probability of Y10 depends on Y1. Correct? If these two were the same, unconditional probability same as conditional probability, then the events are in, remember this, probability of A, if probability of A is same as probability of A given B, then we say A and B are independent. Because when B happened, no changes to the probability of A. Right? Probability of A is unaffected by B. Then A and B are independent. But here we are clearly seeing that is not the case. Shrishti has a question. Can you please explain the last part again? Uh, yeah. So at time t equal to 0, stock price is 100. I'm saying y1 is 99. That means after day 1, stock price has gone down. It has become 99. Remember, every day it can go up by 1 or down by 1. Now from here, I'm saying y10 is 110. 110. Can you go from here to here in the next 9 days? Not possible. In the next 9 days, the maximum you can have is plus 9. 1, 1, 1, 1, 1, 1, right? So you can never get this. Given that y1 is 99, I can never have y10 equal to 110. So the probability of this is 0. Make sense? Shrishti, is it clear? Okay, awesome. So what I'm trying to say, I'm modeling the same event, right? Probability of y10 equal to 110, one in unconditional manner, one in conditional manner, and I'm seeing that they are different. If they are different, that means y10 depends on y1. So the same stochastic process, yt is the stochastic process, and it is dependent on past values. The probability of yt depends on a past value. So they are dependent. It is not independent. And in terms of identical, you have to see what is the distribution of entire distribution of y10 versus, let's say, y1. They are very different, right? It's very easy to see what is the distribution of y1, guys. Just what is the distribution of y1? Y1 can be either 101 with probability p or 99 with probability 1 minus p. This is the distribution, correct? This is the distribution of y1. Y1 is a random variable. That is the stock price after 1 day. This is what it can be, correct? And y2, let's not go for y10. What is y2? Y2's distribution would be, it can become, can you tell me the values? Forget about the probabilities. Just tell me the values. What are the possible values of y2? It can be 102, okay? And 100 and wait, it's not, no, don't rush, don't rush. Think a little bit. It's easy, guys. 2 steps. After 2 steps, what are the possible values? 100 to 198. How will it, what is the probability of 102 after 2 days? P square plus 1, right? What is the probability of 100? Who can tell me? After 2 days, what is the probability of the stock price to have a value of 100? Is it P times 1 minus P? Are you sure? Is this correct? 2 times P times 1 minus P. Thank you. Yes. Because plus 1 minus 1 minus 1 plus 1. There are two paths to reach 100. Yes. So 2 times P times 1 minus P. And this one, 1 minus P twice. Down probability. Okay. So distribution of y1 is this, distribution of y2 is this. Do they look identical? Not at all, right? Completely different. Different values are popping up, different probabilities. So definitely not identical. And they are also dependent. I just showed you that probability of a future, random variable of y is dependent on prior values. Okay. Is this clear? Simple things, but very, very important things. Okay. One question, guys. If I add all of these, what would I get? p square plus 2p 1 minus p plus 1 minus p whole square. If I add everything, what should I get? I should get 1, because that's the exhaustive set of values. If you add the probabilities, total probability should be 1. Okay, so let's continue this. Um, yeah, let's answer these two questions, or maybe you know what? Let me show you the animation, and then we'll come back here. Okay, so here is the simple random walk process. This is our x plus 1 minus 1. X, remember, x is the change or the increment. Okay, and then y evolves like this: previous y plus the change. Okay, so this is the walk, and this is the step or the increment. So this is our this is where you are right now. So y0 at initial value of y is taken as 0. You can take it as anything. In our case, the stock price was $100. Here I'm taking it as 0. So you start at time t equal to 0. And this is a simple symmetric random walk. I have taken probability as 0.5, probability of up movement and down movement as both as 0.5. So it is symmetric, right? So at time t equal to 0, the value of y or the walk, your position essentially, is 0. This is where you are right now at time t equals 0. The next time step, what will happen at t equal to 1? What will happen is x will take some random value between plus 1 minus 1. It will take one of these values, either plus 1 or minus 1, with equal probabilities. Okay, and then y would be 0 plus x. So either y would be either plus 1 or minus 1. So let's see. So it took a value minus 1. Step is minus 1. Walk is also minus 1, right? You're here. Another step. Again, you took a value minus 1, so you're here. Now you took a value plus 1. So now you came back to minus 1. So this is how it will evolve. Okay. Now I have seen till 10 observations. These are the steps that it took, plus 1 minus 1, with equal probabilities. Okay. And here is my walk. So this is my original stochastic process that I wanted to model, which is where you are right now. Or you can say, what is the stock price? The value of the stock price. That is what I'm trying to model, my eventual target stochastic process. But I'm modeling this through this increments, correct? The auxiliary process. It's very easy to define or specify the distribution of the step. So after 10 steps, this series that you see, right? It's so picture this is the stock price. I mean, stock price cannot be negative and all that, but yeah. So just giving you one example, to relate. This is called one realization. Okay, after t, so when you are here at t equal to 10, you have the past values from 0 to 10. These values have been realized. Y1 is realized, Y2 is realized. This is the value. Y4 is equal to minus 2. It's not random, these are realized. Y11, next one, is still random. We don't know. We don't know. Let me ask you this. What is the distribution of Y10? Given this realizations, what is the distribution of Y11? Did I say Y11? Okay, anyways, what is the distribution of Y11, which is here? Yeah, kind of Bernoulli, yes. Plus 1 with probability 0.5, minus 1 with probability 0.5. That's correct. So this is one sample path that have been realized till time t equal to 10. I hope you can calculate the distribution of y11, y12, y13, correct? Now, if you are at time t equal to 0, then this is one particular sample path which may happen in future. You don't know. This is one possible sample path that it can take, okay, in future. Let me reset. So let's do another simulation. It's a little bit, should be different. Okay, now after 10 steps, you are here at 4. Okay, these are the steps, and this is where you are at right now. Given this realization, can you tell me the distribution of y11 now? What is the distribution of y11? 5 or 3, equal probability, 0.5, 0.5, correct? Awesome. This is what I want you to understand. Very, very important. Okay, so probability of y11 given y10 is equal to 4 is the two values, 5 with probability of 0.5, 3 with probability of 0.5. Awesome. So yeah, it depends on the past. So that's why I said y is neither independent nor identical. Okay, so that is one. Next, let's do this. Let me reset this. Look at this row. This is where I am recording or specifying the probability distribution after this, at this particular time. Okay. So what all possible values y can take? Distribution of y. This one is the distribution of y for these values, -10, -9. So y can take all of these values, right? It can also extend beyond, but in 10 steps, these are the two extreme. Either it can be -10 or +10. These are the two extremes. It cannot be more than that. In 10 steps, that these are the two extremes, correct? So all of these values would have some probabilities. Y taking these values will have some their own probabilities, correct? And that is a function of time. Okay. At time t equal to 0, you are at 0. Is this random or known? Y0. Y0 is random or known? It is known, correct? Y0 is not random, it is 0. So the probability of y0 equal to 0 is 1. Probability of y0, remember this is the subscript of t, which means at what time you are talking about, right? So y0, that means value of y at time t equal to 0. The probability of y0 equal to -1 is 0, right? Because you are standing at 0 at time t equal to 0, you are here, so the probability is 1. I mean, it's not random, it's known, completely known. So if you are at time t equal to 0, what is the distribution of y1 after one time step? Distribution of y1. Distribution of y1 is, can you tell me what is the distribution of y1 right now? +1 -1, yes. +1 probability 0.5, -1 probability 0.5. Okay, so after time step 1, this is my distribution. So this is a realization where you can be, it's a random realization. I don't know. In future, I don't know. It could be, you could be here, you could be here, but with equal probabilities, 0.5, 0.5. That's the distribution. You cannot be here. 0, position 0 has 0 probability. After one step, you cannot, y cannot be 0. Okay, so this is my distribution. After time, 2 time steps, after 2 days, you could be anywhere. You could be at -2, it could be at 0, you could be at 2. See, these are the values that have probabilities. -2 has a probability of 0.25, plus 2 has a probability of 0.25, and 0 has a probability of 0.5. Why it is double bigger? Because remember, 2 times p times 1 minus p. 2 times 0.5 times 0.5. Okay, this is the distribution. Is it making sense? I think so. I created this animation to put everything as transparently as possible what's going on. After 3 time steps, this is my probability distribution. Minus 3 is possible, minus 1 is possible, 1 is possible, 3 is possible, 0 is not possible, minus 2 is not possible, 2 is not possible. And these are the probabilities. I hope you can calculate the probabilities. We'll do a couple of exercises, but it should be straightforward. Can you see the kind of diffusion happening? The probability was concentrated at 0. Probability of 1 was concentrated at 0 at time t equals 0. As time progresses, please understand, you are still standing at time t equals 0. This is all uncertainty. After 3 days, you don't know. There are many possible values. After 1 month, many possible values stock price can take. Correct? It's the same idea. So you see now the probability is spreading across. These are the probabilities, right? And it keeps evolving. So this is after 10 steps. Minus 10 possible when all moves are like minus 1, minus 1, minus 1. Only then you'll. So whatever is the probability, right? 1 minus p whole to the power 10. That's this probability. And because it is simple symmetric random walk, all the probabilities are symmetric. Everything is equal. Like if you see mirror image of each other. Plus 2, minus 2, same probability. Minus 4, plus 4, same probability. Make sense? Any questions so far? This is the picture you need to have in mind at all times. Whenever you hear the word simple random walk, this is the picture that should pop in your head. Okay? All right. So that is what I wanted to show you. Now let's solve a couple of questions. I had a lot more planned for today, but it's good that we're taking it slow. You guys are understanding. I'm happy. We'll do one thing. I'll not overload you with a lot of information today. Let's continue this tomorrow, second part. But let's see. Let's spend some more time understanding some or solving some questions, and then we can continue tomorrow. So let's do this. Find the mean and variance of the increment, which is in our case x, and the original process, which in our case is y, as a function of t if p equal to 0.5. It's a very basic question you'll be asked in interviews, okay? But you should be able to derive this at any time you want. Like it's so simple, right? You have to do this exercise yourself, and you can pretty much derive everything: probabilities, distributions, mean, variance, anything you want, everything analytically. So let's do this. Arka says mean is 0, variance is 1. Awesome. For which process, x or y? Let's do this. Oh, sorry. Something happened here. Okay. Mean and variance, right? So let's first tackle xt. What is the distribution of xt? Xt, remember, is the increment, right? And it is IID. Doesn't matter where you are, it is always the same. It is plus 1 with probability p, minus 1 with probability 1 minus p. This is the distribution. What is the expectation of x? Value times probability plus value times probability. P, uh, P plus P minus 1, which is 2P minus 1. Since I have already specified that P equal to 0.5, so this becomes 0. Okay, so on an average, I mean, it's clear, it's very, very easy to see, right? Plus 1 minus 1 equal probability. That means on an average it is 0. So no rocket science there. The variance of xt is 1 value minus mean whole square times p plus value minus mean whole square times probability of the value, which is 1 minus p. Okay. So this is why I'm taking p again. Let me take 0.5. 0.5, 0.5. So this is 0.5 plus 1 times again 0.5, 1. Okay, so the expectation of x is 0, variance of x is 1. All right. Now next, what is the mean and variance of y, which is the walk? Okay, defining y in this manner is difficult. I cannot write yt like this because there are so many values of y, right? I don't know where you are right now. So how do I go about it? I can write yt as this y0 plus x1, x2, blah, 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 till xt. That is what y is, sum of steps, increments. Starting with the initial value, you keep adding all the increments. Now, expectation of yt, expectation of a sum is sum of expectations because expectation is a dash. Expectation of a sum is sum of individual expectations because expectation is a linear operator. Thank you. What is the expectation of y0? Expectation of y0. Y0 is a given constant. There is initial value, right? It is y0. Expectation of x1. All xt's have expectation of 0. So your expectation of yt is y0, which means on an average, you are supposed to be exactly where you started with. On an average, you are supposed to be exactly where you started with. Correct? What is the variance? The variance of yt. Now, variance of a sum is sum of variances. Is that statement true or false? Variance of a sum is sum of individual variances. Rishabh has a very good question. Very, very good thought process. So Rishabh question is this true only when the steps are even? Because what Rishabh is thinking is, this is not true, right? So if you are here at 0, after time step 2 only it is possible to come to 0, correct? Plus 1, then minus 1 you come here, or minus 1, then plus 1. So when I'm saying expectation of yt equal to y0, is it always true even for odd steps? Because let's say after step 1, either you are here or you are here, you are not at 0, right? The key idea is expectation, average. Remember, average is not same as the value. Okay, your coin toss head tail, the values are 1 0, but the expectation is 0.5. Can the coin toss take a value of 0.5? No, the average, right? So on an average, still the expectation is 0. This is plus 1. Yes, after one step, you can be here or you can be here. Equal probability 0.5, 0.5. From expectation standpoint, it is still 0 on an average. Although you will never be at 0. Yes, here's the idea, right? It is not necessary that a random variable takes the value of what the expectation is. This is the classic example, right? It is not necessary that a random variable has to take a value which is the expectation. Correct? What is the expectation of when you roll a die? What is the expectation? What is the expected outcome when you roll a die? 3.5. Can the dice ever show 3.5? It will never show 3.5. So that's the thing, right? So your question is very pertinent. I want you to ask this question, okay? Do not hesitate at all. Small things. Nobody tells you in detail. You'll not find all these things in books. It only comes in conversations. When you have these questions, please, I encourage you to ask as many questions as you want. Expectation is always y0, wherever you started with, irrespective of number of steps. Doesn't matter where you are or how much time has passed. Okay. Variance of yt. Variance of the sum is equal to sum of variances only if there is no correlation between them. Yeah, independent is a much stronger condition. Definitely, if two things are independent, the correlation would be 0. Reverse is not true, by the way. But here it is fine. Okay. Now, question is, are all of these independent? Y0, okay, first and foremost, variance of Y0 is 0. So, because Y0 is a constant, not an issue. So, the random variables are all of these guys, x1, x2, x3 up to xt. Okay, what are the correlations between any xi and xj? Is the correlation 0? Yes, because they are IID. Identical is not the thing. Independent is the thing because they are independent of each other. Increments are all independent, so correlation is 0. So I can write variance of the sum is sum of individual variances. There will be no covariance term because all of the correlations are 0. Variance of y0 is 0. Variance of x1 is 1. Variance of x2 is 1. This one. Variance of xt is also 1. How many ones we have? T number of ones. So the variance of yt is t, which is interesting because expectation is fixed y0. The process at a very future time point, right, far distant in the future, is still evolves around y0. Around y0 in the sense the mean, the center of the distribution is still y0. So this is good. But the variance is exploding. Variance of this process, it is increasing linearly with respect to time. Okay. So if I want to give you a continuous version of this, it is not continuous. Please remember, it's not continuous, but this is what it is happening. It helps you to visualize. So initially, the distribution is concentrated here. As time progresses, more and more values are likely. Okay, because the variance, just picture normal distribution, easier to visualize, is t. So if you're looking, what is the process after 10 years, right? So many steps. 10 years, these many steps. So the variance is 3650. That's the variance. That means you're looking at a huge dispersion. Okay. All kinds of extreme values are likely. Just imagine that the picture, that animation we had, remember, with time, more and more extreme values are becoming likely, correct? With small probabilities. Question from Rishabh, there is a correlation between y0. No, y0 cannot have correlation. Y0 is a fixed quantity. Y0 is known. You're standing there, it is given to you. It's not a random variable. You can only have correlation between two random variables. Does that make sense? Y0 is not random. You can talk about correlation between these two, but you cannot talk about correlation between this and this. Okay, makes sense. So please remember, random walk process has a constant mean y0, but variance scales linearly with time. Okay. Next, we had another question, right? Let's see. Let's solve this. What is the probability of y2 equal to 102 and y5 equal to 103 given that the initial value is 100? How do we solve this? There is an AND condition. It's a joint probability. The question is a joint probability, also conditional. It's a conditional joint probability. How can we solve this? If the initial value is 100, I'm saying what is the probability that after 2 steps it becomes 102 and after 5 steps it becomes 103. So let me do this. Let's first address this condition. Because all the steps are independent, right? I can multiply. So first let's find the probability of reaching 102 after 2 steps, which is nothing but p square. There is only one way to get to 102 after 2 steps. Up, p square. And from 102, it will go to 103 in the next 3 steps. From 102, it will go to 103 in the next 3 steps. What are the possible paths, guys? Hundred and two to 103. Can you tell me a few paths that will take me there in the next 3 steps? Down, up, up. Okay. Up. What else? Up. Yeah, so you got the right idea. Basically, of the 3 steps that I have remaining, I need 2 up and 1 down. Order is immaterial. Does it make sense? If I get 2 up and 1 down, that will give me overall increment of 1, which will take me from 102 to 103. Right? So out of 3 steps, I need 2 up, 1 down. How do we calculate this probability? Binomial distribution, remember? 3C2 up needs to happen twice, down needs to happen once. Binomial probability, number of trials is 3, number of success, pretend up is success, probability P. I need 2 successes. This is the probability. 3C2, out of 3 steps, choose any 2 as that needs to be success or up. And the remaining one needs to be down. This is the probability. Okay? 3C2, P square. These are all interview questions. Okay? I'll give you a lot of practice problems. You have to practice them before the next class. Otherwise, you'll lose out. Okay, so what is this? Let's simplify. P square times 3C2 is 3. Okay, the way I do this is 3C2 is same as 3C1, right? And any NC1 is N. So 3C1 is 3. We have P square and then we have 1 minus P. So overall, we're getting 3 P to the power 4, 1 minus P. This is the answer. Now let's do this one. Think about this a little bit and tell me. Initial value of y is 100 at time t equals 0. What is the probability that y2 is 100 and y4 is 103? Wow, Ritesh is fast. Ritesh is saying it's 0. Do we all agree it is 0? Why is this 0? It is inherently, if you look at these two conditions, is a conflicting condition, correct? I mean, from here to here is possible. +1 -1, -1 +1. Both will lead to same 100. But from here to here is impossible. In 2 steps, y2 is 100, y4 needs to be 103, right? The next two steps, you can never go from 100 to 103. So this is 0. Okay. All right. So I'll give you one homework for today, which is remember the animation that we saw. Find out the probability of yt, capital Y, sorry, yt taking a value small y. Uh, yeah, this is the question. I want a general formula. The inputs would be uh, t, t or n. Let's do n because this is discrete. It helps to have it as. Let's do this. This is a homework. Please try this. Okay. Probability of yn. So after n steps, the value of y taking a value small y. What is the probability? The inputs would be given n, the value y. If I give you the value and the number of steps, you should be able to give me the probability. And y0 is 0. These are the inputs. What else? Oh, there is one more input, p. The answer will depend on this. Okay. So initial value is 0. And you figure out the probability of yn taking a value y. General formula. Okay. Please don't do chat GPT. If you want to learn stochastic process, do not do chat GPT. There are chances you'll get a wrong statement, wrong calculations. And if you learn that, it will be very difficult for you to unlearn. Okay. Anything you need, ask me. Refer to textbooks. Do not do GPT at the moment. Okay. All right. So this is your homework. Let's see. I think this is where we should probably stop. It may be too much. Let's see. Yeah, let's continue the discussion now about stationarity, Markov, filtration, adaptation, and some other processes tomorrow. Okay, let's stop here. Um, we will gradually speed up, but it is absolutely important for you to understand the building blocks. For now, the first stochastic process that we looked at, a very meaningful stochastic process, is simple random walk. And I would request you to, if you want to do additional research, please go ahead. I mean, look at other videos. Stochastic process is something that is abundant in literature, so there is no shortage of material or questions. So if you want to, feel free to do more research. But yeah, let's stop here. So absorb the simple random walk process, write down the expectation variance, do everything by hand yourself, so you become independent. Okay, and then we'll continue with this stuff tomorrow. All right, let me stop the recording. We can discuss.